Welcome to Efficient Workflows. My name is Alex Wilson, and I'm presenting with my co-host Aniket Dikshit today. We will be talking about some of the work we do in the digital practice group at KPF, namely the facade systems that we work on. And then we'll jump into a workshop where we explore one of these workflows, namely using adaptive panels and Rhino.Inside. The case study for the workshop is actually the building just behind me, which is a project I worked on named TCC Hungzhou. So let's get started.
Cool. So that begs the question, who are we and why are we presenting this? So I am Aniket and I'm a computational BIM practice specialist at KPF. That means I am operating in Revit, Rhino, Rhino.Inside, Grasshopper, and similar a whole day, every day. And I'm developing scripts to automate generally the more quantitative aspects of the architecture practice. I still believe that qualitative aspects cannot be automated. That still needs to be a trained architect making those decisions. But I'm more than happy to have that discussion later with people who they carry an opinion otherwise. So yeah, that's pretty much me.
My name's Alex Wilson. I'm a senior BIM specialist. I did my architectural training and masters in Melbourne, Australia before moving to New York to test my kind of own ideas about density. My training and also professional work is kind of centered around urban design and super tools, which is why I really enjoy my job at KPF. And in terms of workflows, very similar to Aniket, I really enjoy, kind of emerging technologies, computational work, and kind of interoperability, so jumping between different softwares. I guess at this point, it's also should be noted if you're kind of looking to get into design technologies, always take a photo looking to the left. Aniket and I both did that, and it's really helped our kind of careers so far. So definitely recommend that.
Cool.
Also, if you have any questions, feel free to unmute. This is, a reasonably informal workshop. We are kind of going to jump through a lot of slides. So we are going to try and keep it moving pretty quick, but, feel free to either use the chat or just unmute if you have anything you'd like to say. And we will kind of pause for a little bit between sections. So if you, if you feel like you don't want to interrupt the flow, but have a question, we'll stop kind of in between some of the sections and you can ask then.
Awesome.
Okay, so we're part of the, we kind of sit under the KPF BIM umbrella. The KPF BIM umbrella stretches over the world. We have multiple offices in different countries, as well as different teams. So Aniket and I work out of New York, and we have a team in London, which supports the London office. And we also have a team in Singapore, which supports some of our Asian offices. I guess at this point, it also should be noted that London is looking to expand their BIM team currently. So if you know anybody who is looking to kind of join a digital practice team, please kind of reach out to either myself or Aniket. I believe the deadline is pretty soon. They're kind of interviewing people at the moment, but if you know someone who's super excited about, all things BIM and interoperabilities and computation and anything kind of like that, just let us know and we can pass it on to Martin over in London.
Awesome. Yeah, just the idea that KPF is always working, always keeps me entertained that we're 24/7 just working on our projects.
So another kind of important thing to notice is that KPF, the umbrella that we sit under is Digital Practice, and it's not Revit Help Desk. So when we're engaged by teams, we work directly with the teams to, analyze their designs, speed up their workflows, create kind of custom scripts. And we are also all trained architects. So we're not tech support. We do have a help desk to kind of address tickets, but we're not just sitting back kind of waiting for things to break. We take a very proactive approach to really work with the teams. And we are all architects as well. So it's kind of just important to note that we're like digital practice, we're not Revit Help Desk.
Cool. So as part of our KPF digital practice, there are 4 streams that kind of come there. One is computation, the others, all the Streams being computation, BIM, visualization, and makerspace. And we're all specialists operating in there, creating workflows, researching and developing different scripts to automate the boring tasks, or things that just are more quantitative in nature and less qualitative in terms of mind application. So this is just kind of a GIF that shows on all the latitudes that we operate on.
And also, I guess it should be noted that yesterday there was a great presentation by Pingxing and Brandon, which is another two specialists. Brandon works for KPF UI and Pingxing works for Applied Research. So I'm not sure if you guys got to see that yesterday. I'm sure the YouTube will be uploaded soon, but it was a really interesting presentation on Rhino Compute. So shout out to those guys. So tech stack today, I talked about it a little bit beforehand. While we were just kind of sitting in the lobby waiting to kick off, but we'll be using Revit 2020. The files also can be upgraded to 2021 or 2022 if you prefer to use those. Rhino 7 and Grasshopper for Rhino Inside, and also, sorry, Rhino Inside. So please make sure you have all these installed. We'll be doing kind of a short presentation before we kick off the workshop itself, just to give you guys some time to kind of download the files. There's also the workshop files. Aniket posted that in the chat. So if you haven't downloaded those yet, please do so. This workshop will be reasonably fast paced, and we won't kind of be building everything. We'll be more talking about kind of general overarching principles of design, and then a little bit of how to, but ultimately we'll kind of take leaps. So at certain points we'll be advising you to just open file X or something like that. So make sure you've downloaded those files, you have them on hand, just so once we jump into the workshop, you can follow along very easily without kind of missing out on stuff. Okay, so the class.
Oh, it's me?
Yeah.
Oh, sorry. I just got sidetracked. So the class summary is more on the lines of we're going to be inside of Grasshopper and in Revit space. So we're going to create some kind of information inside of Grasshopper and for paneling and similar, and we're going to utilize that information inside and push that information into Revit to create different paneling types. We're going to go into more detail as to how the workshop breaks into different sections as we move forward.
Cool. So kind of like Aniket said, just in a little more depth, we're kind of going to start with an introduction. We talked a little bit about ourselves in digital practice. We'll talk a little bit about KPF as well and some of their work. Then we're going to basically use some of the KPF buildings as data points to analyze the way that we worked on those facades, interesting parts of those facades, lessons learned, and as starting off in kind of simplicity and then building the levels of complexity as we go down the projects. Also, that kind of works in a little bit of a timeline of some of the KPF Revit projects as well, which is reasonably interesting. Then we'll jump into the workshop using one of the buildings as a case study to talk about adaptive panels and Rhino Inside. And then just kind of finish with some resources as well as, a discussion, any questions, and also our contact information if you would like to, discuss any of the things we talked about further.
Alex, can you send Rustam the link to Slack channel? That is for the workshop. It should be in the email.
Sure.
Okay. Cool. So
I'm sorry, guys. Sorry to interrupt. Yeah, there is a link in the email, but it's not linking to a specific channel. It's just to the general AECtech workshop.
I think that is.
That's enough. Maybe never mind. Then we could just.
In case you have any questions, you can just unmute yourself and ask, or just ask it in the chat. We don't mind that. If you prefer, if you don't mind doing that.
Okay, thank you.
Cool, awesome. Thank you, Rustam. Cool. So our learning objectives for this workshop are gonna be what are the different methods for facade modeling inside of Revit. We're gonna learn how to select an appropriate method based on a decision matrix. Like, should it be a system panel? Should it be a custom modeling custom panel? Should it be an adaptive panel? Then we're going to kind of graduate into learning how to use adaptive panels inside of a complex facade design. And lastly, the overarching goal is how to place those adaptive panels inside of Revit using Rhino.Inside based on information that was created inside of Grasshopper or Rhino.
Okay, so the assumptions, just kind of a few, general things to discuss. We're assuming everybody on the call has a general familiarity with Revit, that you are familiar with curtain walls as a basic system. We're not kind of going to be discussing, how to divide by length or by number, things like that. And you have a general idea about unitized facade construction. You don't have to be a detailing kind of wizard. It's not going to be a detailing workshop. However, a general understanding, kind of the same with everything in Revit. If you understand how it's built in the real world, generally there's going to be ideas inside that of how to build it within Revit.
Awesome. So that begs the question, who is KPF, right? So KPF was founded in 1976 on 4th of July, and it has offices in 9 different locations throughout the world. We are the architects for 6 out of the 11 tallest, well, I believe it's 12 now, 12 tallest completed buildings in the world. We have a staff of 670 plus that's operating all around the world, which is led by 77 directors and principals. And we are a high award-winning practice. We have 350 plus design awards plus 100 plus green awards. You might know us from one of these famous projects. The one in the center being the One Vanderbilt, which is located on top of the Grand Central Terminal. And Alex, if you want to speak about the other 2 projects.
Yeah, so the other one is the Shanghai Financial Center and also the Heron Tower in London. So I guess kind of some things to take away from this, especially the super talls number, is we do a lot of very tall towers, and pretty much all of those use curtain wall systems. Whether or not that's curtain walls, generally it's both curtain walls in the architectural sense of the word and the Revit sense of the word. But if you see it's super tall, there's pretty much a coin flip that it was designed by KPF. So we do a lot of really tall towers. A lot of those are glass, all of those use unitized systems. So that's just kind of the resume to understand, I guess to give us some credibility on why you should, why you're here and the kind of work we do.
I'm sorry, Tim Lee was having issue accessing the workshop files. Give me a few seconds, Tim. I'll send you the location for the files again. Yeah, no worries. So going on to case studies.
Okay, so this is kind of the second part of the introduction. This part, we're just going to analyze a number of different KPF buildings. Basically increasing in complexity of facade systems and also workflows within Revit. And we're kind of going to be looking at them and analyzing them through the lens of the facade itself, the panel design, and the mullion design. Ultimately, at the end of this part, we're going to be reviewing a basic ideas matrix, a decisions matrix, which would allow you to take theoretically any design, and then at the start, kind of answer a few questions, and end up with a system that you can proceed in Revit. It's obviously massively oversimplified. So while it is kind of a decent framework for looking at any design, obviously within Revit there are a number of ways to build anything, and so just take it with a grain of salt, and don't email me if you use the decision matrix and then your Revit file crashes. So let's start off. This project is project A3 in the now very famous Wuhan. For this part, we're really just looking at the white double curved surfaces. So this project is a number of years old and was before the introduction of Rhino.Inside. So for this, the shell itself, which is a glass fiber reinforced concrete, is done as a Rhino file. The project was designed using Grasshopper, and then kind of afterwards was manually molded within Rhino itself. At that point, when it broke from Grasshopper, it was kind of a little bit hard to replicate that using adaptive panels and also the high rate of change of designs. So this is just an SAT file that's brought in to Revit itself. Now, it's important to note that when we use SAT files, we always link them. That allows them to be updated very easily. It's also important to note that SAT files, you can only use a single material. If you're looking for more materials than one, you either have to use multiple SAT files or look for another one. And it's just a single system. So obviously single material, single system, and it's a monolith as well. So now there are kind of some other options that we might look into, and we'll kind of discuss some of those later. But this is just an interesting example and an interesting form. It's quite complicated. However, you can see in the Revit screenshot in the bottom left, it cuts very cleanly. Also, a kind of interesting thing that the team did here was that the joint lines you can see in kind of very light gray aren't modeled. So to reduce the polygon count, the surfaces itself are a single SAT. However, the joints are AutoCAD. So there were a number of kind of iterations of paneling that was just sliced up in Rhino itself, and then a 3D AutoCAD file was brought into Revit to allow the joints to be displayed in elevation and 3D. This just massively increased performance rather than slicing up all of the geometry itself.
Yeah. One thing I believe also we've done when bringing in SAD is that we always bring it inside of a generic model. So that allows it to cut perfectly. This is something we have learned while doing one of the multiple curtain wall panel situations and playing with the Rhino geometry over the years. Awesome. So the next project is the 17XM. This is a fairly simple building that kind of resides in the DC area. A lot of the nuances of the design come from the slight angular facades. So none of the corners are meeting at 90 degrees, which meant that we had to kind of build all of the facades as custom panels and to allow for clean joining conditions. There's also a fin situation happening all over the facade, which was kind of, the design was changing at a pace that it was difficult to replicate inside of Revit. So there was a dynamo solution that was available for the team. And this is kind of early Rhino.Inside, when Rhino.Inside was kind of not that very stable, which allowed the team to, not manually place the fins on the curtain walls, which we're going to also do in the workshop later today, just to see that how we can automate that. The panels were fairly simple. They were all rectangular coplanar panels, nothing really complicated happening there. And yeah, we broke ground for construction earlier this year for this project.
So the second loadable family example is the Chang Tower, also located in Wuhan. Here you can see the kind of, from the panel in the bottom left, the complexity starting to increase. We have, backing panels, back pans. We have extruded systems for the mullions themselves. At this point, the mullions are now fully integrated into the panel themselves. This happens kind of very regularly. We very rarely use mullions within the curtain wall systems. Integrating them within the panel themselves just allows you to do mitered joint conditions, multiple materials per mullion, multiple extrusions on the profile, things like that. It's a vertical facade. There's no kind of slanting or sloping. There is some 3D play in the facade. You can see at the crown, although it's not a very clear screenshot, it goes from a flat facade into a chevron and through a three floor kind of changing of the facade. This is all kind of done just using basic loadable families, curtain wall systems within Revit with a division by length, and there is a kind of varying spandrel condition, which is just a type parameter. It's a fairly repetitive building. So we just kind of used Revit. I think an important part of this presentation is to understand that we really like to use software for what they're good at. So Rhino is very good at kind of double curve, things like that. But it doesn't mean that you can't just use straight out of the box system families or loadable families. A lot of the examples do use that because it's kind of important to really utilize what software is good for.
Awesome.
The next example is 30 Hudson Yards and 10 Hudson Yards. So these are the projects which are quite well known. They're located at the top of the High Line. And KPF was also the district architect for the Hudson Yards development, so that involved kind of a lot of coordination. You can see that this also uses loadable families. Now, this project has been in the office for a very long time. You can see there that there's actually not only is the facade itself slanting, but the panels themselves slant, so they're actually stepping as from floor to floor. This project used loadable families also. However, you know, looking at it, I kind of wonder whether or not adaptive panels would have been a good way to go. However, one thing that's very important to note is that when you're designing a system for a team to pick up and run with, you have to look at the skill set within the team. Adaptive panels are, while they're incredibly adaptive by nature, they're also more complicated. So it's really important to select a system that allows your team to kind of take that and really implement it over an entire project and own that system. You know, that's really important as a design technologist to understand the, you know, the workability and of the workflow that you're creating, because if you create like the world's greatest adaptive panel, but you're the only person that can use it, there's it may not be the best kind of solution to look for. So Hudson Yards, slanted varying conditions, slanted walls, slanted panels. So there were type parameters built into each of them. And for the mitered corners, this was done using a void. So if you have a void, you know, just a mass kind of within Revit itself, you can slice panels, which will give you kind of miter conditions. It's not really the cleanest way to do this. And another thing is that if you slice a curtain wall panel with a void, Revit's areas will still believe that part of the panel exists and count it in areas. So if you are doing material takeoffs, which we don't really do, but is possible within Revit, you will get some kind of interesting results, we'll say, where Revit believes that the extra part of the panel still exists, even though it doesn't appear three-dimensionally. Okay, back to A3. So now we're kind of moving away from flat panels into curved panels. These are vertical curved panels, so not slanted, although we will get to those also. This is one of my favorite slides in the presentation, and the reason that this is one of my favorite slides in the presentation is it returns to an earlier comment I said about workability. When the team came to me with this problem, which is how to create a curtain wall panel for a building with multiple radii over the entire facade. So here you can see these glass panels, which kind of wrap in between the glass fiber reinforced concrete. They're all curved. The glass is curved, and there's not a consistent radii. So while certain arcs share the same radii, they all have different ones. So along what appears to be the flat facade, it's actually a very gentle curve, and then it kind of, the radii number decreases as it kind of wraps around corners. The system I came up with was to build a loadable family, which has a arc in it. You can set the radii, it flexes itself, it has mullions in there, and I thought it was a pretty good solution. The solution the team came up with, which I think is better, which is why I'm presenting that instead of mine, is they used walls. So within curtain wall systems, you can actually use a wall itself as the panel. Now, the advantages of that is that a wall within Revit, when loaded into a curtain wall panel, will take the radii of the host itself instead of faceting like a loadable family. So what that means is you can just draw your curtain wall as an arc. You can then change the panel to a wall, and the wall will follow the arc. Now, the issue with that is if you're using out-of-the-box mullions inside of Revit, they will facet. So your glass will be curved. However, the mullions along the bottom will facet. So the solution the team came up with was they used wall sweeps within the walls as the mullions. This allowed a couple of great things. The first thing, wall sweeps obviously follow the wall, so they're going to be curved. They're not going to be faceted. Second is it allows you to, in a certain kind of way, create a type parameter for the mullion location. It allows you to set the wall sweep height based off the wall itself instead of as an instance parameter, which is kind of the downside of using system panels instead of loadable panels. So I think this is like a very kind of creative solution to creating curved panels. And when I saw it, I was like highly impressed with this team and how they came up with it, and then the adaptability and implementation over the entire building. So I think this is a really innovative way to kind of use some of the things within the software itself to solve a complicated problem. One Vanderbilt. So now we are stepping away from loadable families and into adaptive panels. As we mentioned before, adaptive panels do have a skill barrier to entry. They're not extremely complicated. However, you do kind of need to be very you need to kind of have a little bit of practice. They're hard to give to teams with no experience and then just expect them to be able to run with it. This project's One Vanderbilt, as Aniket mentioned at the start. It is just down the road from our office, so we were lucky enough to see it get put up before we started working from home. It's slanted in all directions, so the facades kind of step in. And the panel is flat, unlike the Hudson Yards projects, and there are kind of repeating elements within the panel. So you can see there's a terracotta spandrel condition, as well as metals and fins. For this, it was done using adaptive panels and then Dynamo for placing. So this, a lot of repeated elements, varying floor to floors, repetitive elements, things like that, and mitered corner conditions. When you're looking at a project with features like that, adaptive panels, especially with the sloped walls, can be a really good solution. This allows you to, only have a single panel or a few different panels. Obviously, your mech floors aren't going to have glass, things like that, and then just building the system within the panel, implementing the panel, and letting the adaptive nature of the panel itself create the variation over the facade. The next project is Westlake 66. This project only used adaptive panels. You can see from the kind of overall Revit facade, it's quite a large project. It has a number of different facade systems and a number of different panels. It's been in the office for a number of years. It was started before Rhino.Inside. The team is extremely capable in Grasshopper. The facade system was entirely driven out of Grasshopper. Not only the facade system, but also some of the stair designs, things like that. From there, the project also, it basically took that data from out of Grasshopper, exported it to Excel, and then brought it into Revit using Dynamo. I think Wenchen, who is the mastermind of the Grasshopper, might even be on the call. So, shout out to Wenchen. She is. Yeah. Cool. Yeah. So Wenchen on the call was the Grasshopper mastermind behind this. These adaptive panels are vertical. So they're 4-point and 6-point. What I mean by 4-point panels is there are 4 placement points for the panels. And the reason for introducing the additional 2 is to create an arc. So if your panel is curved, you add an additional 2 points. So, between the bottom and the top, there's an additional point, which kind of pushes in and out to control the radii. Obviously the advantages of that is you can use the points from Grasshopper to place all of the curves. You don't need to add parameters to adjust the curves, as the placement point of the adaptive panel will set the radii, and then the panel itself by its adaptive nature will flex to create the right location. This is a great project that you can see, like, from the Revit screenshot and even the design itself. Great number of variations, different fin conditions, things like that. Very adaptive in nature. A lot of kind of changing within the panels. Even the podium itself has a different system, which it greatly varies. I really like this project. I think it's extremely interesting, both in terms of the design and also the Revit solution, and also the output of the plans. The team had very high standards for drawings, and I think the plans turned out very well.
Awesome. So on to the next level of complexity when coming into when talking about curtain wall panels is this project, which is 2001 Bell, which is located in Virginia. The complexity here was none of the panels were straight and none of the walls, the joining conditions of the wall were 90 degrees either. So the walls were joining at 24.44 degrees and similar. So we had to do a fair amount of trigonometry to make sure that the joining conditions were happening correctly. And because there were piers involved, you had to make sure that the void was moving in a way that, you know, everything kind of come together perfectly. And since team was using Revit as the sole source of documentation and design tool, kind of everything was put into Revit. So the curtain wall panels were more the normal loadable families, but they were placed and altered and changed. The types were changed using Rhino.Inside. So because there was a certain logic or pattern that could have been, that was designed by the team, we were able to utilize that to alternate the panels inside of the facade, but also for the piers. And this is an exercise that we're going to do today as well. Not in the same complexity, but in a much simpler complexity, to show how we can use structural framing or to be used as fins inside of Revit. So in here, as you can see that even the panels, they were on a six types, which were going from A, B, C, D, E, F, G, and they were alternating and moving up the next one. So we were just by creating that as a data set inside of Grasshopper and using that as inputs, we were able to change or place these piers or fins inside of Revit using Grasshopper. And that reduced just a load on the team so that they didn't have to export an Excel from Grasshopper, from Rhino, design in Rhino, export an Excel in Grasshopper, absorb that Excel in Dynamo and replace that inside of Revit. And as we all know, like Dynamo's geometric calculations aren't the best. So we were able to utilize Grasshopper for what Grasshopper does best, which is analyze, geometric based calculations. So that allowed us to actually deliver this project in a much better and faster and efficient way than I thought, well, when I first came onto the project, because all of this was being done manually by the team, which seemed quite a waste of time at that point, because they would have a design change the day of the deadline and they would just spend so much time like fixing the design in Revit.
Okay, TCC Hungzhou. So TCC Hungzhou was our first Rhino.Inside project, and also one of my first projects within the office. This is where the complexity really starts to jump up. This facade system is slanting in elevation and also transitioning to a horizontal, from vertical to horizontal. You can see at the bottom, it kind of folds down. Although it's still a single system. So obviously, you know, out of the box curtain wall solution isn't really going to work. It also should be noted that it has flat panels on the major faces and then curved panels on the corners. Now, these curved panels are actually sections of a cone. The fact that the facade itself is slanting back means that filleting that radii means you have different fillets at the bottom and the top. Also, because of the way that the facade is designed, you have vertical mullions, or well, slightly slanted vertical mullions, I guess, technically, on the major facades. Then below that, the horizontal mullions do not respect the tangent of the facade itself. The horizontal mullions respect the floor level, the vertical mullions respect the facade. So you have a difference in kind of mullion logic built into the curtain wall panels themselves. We also have a patterned thin solution on the facade itself. So on top of that, you have, you need to be able to create a system which is very kind of adaptive for the team, as Aniket was saying with 2001 Bell. So in this, we actually split the fins off and use structural columns instead. Structural columns are a great solution. We'll talk about that in the workshop. There are over 9,500 unique panels within this project. So using adaptive panels was great because it allows us to set up a kind of logic for a single single panel and then implement it over entire facade. We used Rhino.Inside as the placement method, just keeping everything in the same ecosystem. It was also, the first Rhino.Inside project within the office, so the technology was really new. We were really excited to kind of have a play with it, and this seemed like a great example. And then there are also mitered conditions. So as I was talking about the structural mullions behind that for this unitized system, on the curves, you had mullions that were using tangents instead of just straight offsets. So it's an extremely complicated facade, which ultimately created a very interesting solution. And this building is the building we're going to be looking at as a case study for the workshop. So just keep it in mind. We'll talk about it a little bit more in the workshop.
Rustam has a question which goes around, how didn't the client have problems with manufacturing 9,500 plus different panels?
That is a great question. No, not really. I'm not entirely sure. It's actually going through, the team's going through shop drawings now. Luckily, I'm not someone who has to go through the shop drawings of 95,000 plus different panels. However, it never really came up. There was a QA/QC process. Sorry, not QA/QC. There was a VE process. However, it never really came up. For this project, Taiwan Concrete Construction, I believe is what TCC stands for. This is their first mainland tower. So for them, it was very important to create a very unique design, and they were fine with it. I definitely agree. A good part of design technology is creating kind of complicated forms that can be built out of very simple methods. This tower is not one of those solutions. This tower was an insane number of unique conditions, and the client group was absolutely fine with it. So yes, I totally agree with you. It's interesting in a way that it kind of goes against some of our nature as design technologists to try and optimize for constructability, but this project was not that project.
Yeah, and I believe we need to give kudos to Nick Despians, who's on the call as well, for holding a lot of the ground for TCC, I believe, Alex.
Yeah, Nick. Nick is the head of digital practice at Python Whiz, and created a lot of the Grasshopper side of this facade with the team.
Cool. So one of the last case studies that we are going to be showing is the Perfect Auto Center. This is still a very early concept rendering slash the project is still in the concept phase. So a lot of this, what you're seeing here is just what we're trying to do is we're using Revit for what Revit is good, that is documenting, and we're using Rhino and Grasshopper for the design process. So this has allowed us to, Rhino.Inside has basically allowed us to seamlessly transfer all of these facade conditions into Revit. They've not gone through a V process yet, so the facade is insane. So it's like 700 different panels, all doubly curved, all not even radial to a point. They're all based off a different grid projection, which leads to all of them curved in a different with a different radii completely. But they're all going to go through this. This is much early on. They just completed their 25% or 50% DD. So we're gonna it was just to showcase that we're using Rhino.Inside even for transferring projects that are much early in the concept phase into Revit to document inside of Revit. And this has allowed us to, utilize each of the softwares to kind of do what they're better for or good at. So yeah, that's pretty much it in terms of case. No, sorry, I jumped the gun there.
Yeah, one more. The last one is MKS Beam. So this was Westlake 66, which is in Aniket's background, and we talked about it previously with the 4 and 6 point adaptive panels. MKS Beam is a kind of a very great one-click solution from transferring data from Rhino to Revit. this is obviously isn't a facade, it's a stair, but it should be noted that stairs can be extremely annoying for like, designing, doubly curved stairs, things like that can be extremely annoying in Revit. So for this, we use MKS Beam. Once again, very heavy grasshopper team, very heavy in the design space. This stair, I believe, is still going through design iterations after the 3rd addendum after construction. And, Beam, I believe MKS are also presenting here. I highly recommend, if you have a chance, to check out their presentations. If you haven't had a chance, definitely look into that company. Really, really interesting stuff that they're developing, and very, very simple for users to use. You can see here left and right, Rhino and Revit screenshots. It's a very, very simple way to add families to Revit, place them, update them. It allows for blocks being transferred to loadable families. It allows for adding subcategories, adding materiality to the families themselves, and then updating that in Rhino, repushing it through Beam, and having it update automatically in Revit. It's a very elegant solution, and for someone or for teams who don't really like diving under, getting their hands dirty with Grasshopper and Rhino.Inside, it's a very simple way to kind of transfer geometry. And in some instances, it actually can deal with geometry a little bit better than Rhino.Inside. So yeah, highly recommend checking out MKS Beams. We've used it for stairs, we've used it for facades. Unfortunately, some of those facades aren't quite public yet, which is why we're showing the stair example. But yeah, it's a great solution, and check out their talk if you have a chance. Sorry, I was just trying to read the chat and present at the same time, which is a little, which I'm not so good at multitasking.
Do you want to answer the question?
Yeah, so the question about the facade documentation, I believe that was in reference to TCC. We took control of the design all the way through CDs. However, the panels themselves were documented, I believe, by shop drawings. We didn't issue individual drawings for every single panel. We did issue the Revit model. The LDI based in China also used Revit, which was great because a lot of LDIs only use AutoCAD. And then I believe it was sent out for shop drawings. Like I said, I didn't have to review them. And since the project has kind of started to wind down, the team has kind of minimized. My work within the team has dropped off a little bit. So I'm not entirely sure how that was done. However, I don't believe we did shop drawings. We documented every single panel. For some of the other projects in the office, we have used Rhino to help generate the facade documentation. For example, the Wuhan project, which you can see on the far left here, that, organic curved sweeping facade. We were looking at a solution for using Rhino to document the profiles at each of the panels. So basically slicing it up using Grasshopper, getting those profiles, placing that on sheets, documenting using that to kind of help aid the team, just like accurately describe the construction method used for these panels. And then them being sent off. So we've actually had some tests for that constructed at the moment. It looks phenomenal. So in TCC, to answer your question, I'm not entirely sure how it was done. I believe it was probably just, manual work done out of the LDI's office. However, internally, we are kind of exploring some methods for using Rhino.Inside and Grasshopper to aid the documentation of our, highly adaptive facade systems, although I'm not entirely sure what happened on TCC. Rustam's question, the reason unless you document, I was just curious. Oh, okay, yep, cool. Great. Okay, so this is kind of the design matrix that I talked about a little bit at the start of the presentation. Obviously, it's massively oversimplified, and we're kind of drawing towards the end of the first hour, so I'm not really going to jump into it too much. One thing I would like to talk about is under the monolith, there is the void solution. So if you're looking at a monolith facade, there's the positive, but then there's also the negative. So if Wuhan, the white kind of sweeping thing is the positive. For a negative solution, you may have a kind of highly organic form that is cut out of a Revit a Revit wall. For something like that, you're basically just doing the opposite of Wuhan. We have a project which is confidential within the office that uses basically Rhino.Inside to create voids, and then they cut walls. Like we've kind of talked about, using things that are good, using software for what they're good at. If you have a wall within Revit, you know, you have all of the positive aspects of using Revit walls. For example, the fact that you can change the structure, it'll cut well in plan. If you were looking at taking a, you know, doubly curved wall, like a single curved wall with voids out of Rhino, you're not going to have all those kind of advantages of using detail levels, things like that. So if you do have kind of a complicated repeating void situation, maybe look at using Rhino.Inside to create your voids, optimizing the points so it's not too heavy, bringing those voids into Revit itself, and then cutting just a sister wall. But yeah, this is just kind of something we'll be sending out this presentation, so something to review. It's also kind of interesting to note that although it kind of looks complicated, if you jump down to the single mullion, that's just basically system walls in Revit. So if you go massing, unitized, vertical, flat, division by length, and then single, that's just out of the box. So, you know, that's something we use a lot. We do talk a lot about, you know, different workflows, things like that, but sometimes out of the box solutions are the best, or can get the job done very easily.
We can move forward.
Yeah, well, actually, at this point, does anyone have any questions?
Yeah.
Or if anyone would like to unmute, you know, feel free. I think this is just before we jump into the workshop. So if there's anything you'd like to kind of talk about, please unmute yourself and feel free to ask questions. Awkward silence. Great. Okay.
Speaking into the void.
Yep.
Cool. All right. So
we'll help you not make it fully a void. We are listening. We love what you're presenting. You know, keep going.
Thanks, Timon.
Thank you, Timon.
You bet.
Cool.
It's so hard to present to the void sometimes. And we all, you know, we're here. We love this. Thanks, guys. Keep
Thanks,
going.
mate. Thank
Awesome.
you.
Thank you, Timon. Awesome. So now we're gonna get into the workshop part of the session. We're gonna be utilizing a lot of technologies which we're gonna cover in the next couple of slides. So the first thing that we want to say is there might be some amount of live Grasshopper scripting. We've kind of not done anything that is text-based coding. We've tried to keep it as simple and easy to understand as possible, but there might be still some wires that you might be asked to connect. And as life goes, Murphy's law is in place. Anything that can go wrong will go wrong. So bear with us while we try to troubleshoot that situation, or if it happens on my screen or Alex's screen, while we try to troubleshoot that on our screens. So yeah, we appreciate your patience further. This is a reminder for the tech stack. So we are going to be using Revit 2020 or above. Alex and I will be doing all of our demonstrations in Revit 2020. We would again ask you to download the latest version of Rhino 7, which probably is 7.8, because we've seen both ways where Rhino.Inside is too new and Rhino 7 is old, and that doesn't work, or the other way around. So make sure that you have, hopefully by this point, you already have Rhino 7, Rhino.Inside, and all the similar situations up and running for you. And then we can get into more details. Cool. So thank you, Alex, for reposting the link. So the question is, why Rhino.Inside, right? Like the kind of the technologies were already present for us to do what we're supposed to do, and why should we go down the route of Rhino.Inside? Well, in the earlier process, what we were doing at least 3 years, 4 years ago was designing in Rhino, taking that information out using Grasshopper, exporting that to Excel, then reading that Excel inside of Dynamo, and then putting it inside of Revit, realizing it doesn't work, going back to Rhino, fixing it again in Rhino, going through the whole process again, and back and back and back, and which, as you can understand, is an extremely tedious process. So that's the reason when kind of Rhino.Inside came into being, and it's an integrated system where everything is inside of a single ecosystem. We grabbed at Rhino.Inside with both hands. and we decided we're going to use it for as much as possible. So hence the Rhino.Inside. So when we are going to be exploring design, we can see a lot of that design already happening inside of, the Rhino space. And then when we decide that, it's now ready to test something, we can test that inside of Revit.
Cool. Okay, so TCC, this is going to be the case study that we're going to look at. It was our first Rhino.Inside project. It has curved panels, slanting panels, vertical panels, horizontal panels, patterned facade fins, things like that. So just a little touch base to the earlier part of the presentation.
Cool. So go ahead, sorry.
So the process, just to kind of, as a very quick overview, we're going to look at adaptive panel. We're going to look at Rhino facade division, adaptive panels, adding complexity to both Grasshopper and the Rhino and Revit, and then kind of ending up at the very end with a facade that has, fully adaptive panels. It's we kind of wanted to look at more of a real world example, but however, keep in mind, this is more of a planting the seed of the idea. So while the facade itself at the end is, kind of a reasonably typical facade, you can take this in really any direction you're looking to take it. Adaptive panels is really its own world. And so just kind of introducing some of the ideas rather than, creating a crazy facade, although that's what you really want to use adaptive panels for.
Awesome. So the key takeaways are the knowledge inside of Rhino that we're going to be using. Grasshopper is, we're going to create like a very basic geometry, and we're going to create divisions for the panel in there. And then we're going to create some kind of information. The easiest way I could think of to create information was using an attractor point. So we're going to use an attractor point to create some kind of information to kind of feed that into Revit. There's one tip that I have for everybody on the call is, since Revit is a single threaded software, we try to not do anything that's heavy computationally inside of Revit or inside of Rhino.Inside for that matter. For all the sessions that for all the files that are going to be done today in the workshop, they can be opened inside of Rhino.Inside if you have a good enough computer. But for anything that's like majorly heavy computationally, we would ask you to do all of your geometric calculations outside of Revit in the Rhino Grasshopper line, and then take that information and plug it into Revit.
So adaptive families, just kind of a brief overview. They're point-based. They can't be converted to loadable. So if you start with adaptive, don't try and turn it to loadable later. It won't work. You can't jump kind of within the object categories themselves. I really like using adaptive panels. I kind of like the variation, and also like and kind of setting up rules and things like that. I think they're really useful. They also kind of allow you to do curve length or normalized curve length. So you can do a distance, for example, 400 mils, 500 mils, or you can do a fraction of the overall. So for example, 0.2, 0.3 will give you a distance, which is great for kind of some of the slanting panels, and we'll cover that when we get into it. A really important tip for using adaptive panels is everything is work plane based. So I would recommend setting a keyboard shortcut for work planes. So the keyboard shortcut for keyboard shortcuts is KS, and then just search for work planes. I use WW because I like using the same letter twice for a lot of my keyboard shortcuts, but definitely kind of set that if you're going to be using adaptive panels a lot, because setting your work plane is something you're going to use all the time.
Cool. So let's start with the workshop part, and we're right at the hour. So our workshop goals are kind of taking a very basic facade and creating a 4-point panel, extremely basic facade inside of Revit. We're going to be using Rhino Grasshopper first for like the division and the quote unquote design process. And then Alex is going to show how to do the panel inside of Revit, inside of the family environment. And then we're going to go jump into Rhino.Inside to place that panel. And that's going to happen for all three of these. So the second one is more a transom panel with a fin. And as you can see, all the fins are kind of, unique in a manner. So that's kind of that information was created using a tractor point, and we're going to get into a much more deeper end of that as we move on with the workshop. And the last is an 8-point panel, which we'll get into the deeper point of it as well. So at this point, I would ask people to just open the 01 Grasshopper file. It's called 01 Basic Surface Division. In an ideal world, you're opening that inside of just Grasshopper Rhino, not inside of Rhino.Inside. And then we can start dissecting that script as to what is happening there.
We've also kind of optimized this a little bit so that you're not going to be creating 9,500 panels. I guess it should be noted that for that 9,500 panel building, it took about 2 hours to place all the panels. So we're just going to look at like a little piece of that. So yeah, hopefully you have a super powerful computer. If you don't, you know, you'll be okay.
Oh, I just jumped the gun on a slide. Sorry. So yeah, talking about the first is we're going to create and divide a surface. We're going to isolate the points from the divide surface to place basic panels that are going to be created in the next exercise. In the Grasshopper file that you have currently, there's a cluster that kind of reorders the point. We have a very specific way that KPF does. Sorry for all the different screens. Am I sharing the right screen, Alex?
Yep.
The big one?
Yep.
Okay, cool. Awesome. So let's try and dissect the script. What we kind of started with was a curve, as does a lot of the Grasshopper files do. If you open it, I'll generally work with the bifocals because that, you know, just creates a pop-up window showing me exactly what each of the components is. If you're working in multiple different visual coding software, sometimes you get confused as to what it's supposed to look like. So in case you're new to Grasshopper, you can also do draw full names instead of draw icons, and that's going to give you the name instead. But I like the icons because they look cool, so I'm going to stick with the icons. So what we're doing is, it's not at all complicated, right? We're taking a curve, right, and we're just extruding that curve so that that curve is at an angle. What we're doing with that, sorry. So it's so that it's not straight, right? So there's a certain amount of complexity to the panel, to the curtain wall that we're creating. And once I loft it, there becomes our curtain wall. And then we're using the lunchbox quad panels to create, you know, a single floor height of curtain walls. Out of that, we're creating a much higher story so that, you know, a bigger curtain wall kind of comes into place, which you can see here. Really not complicated. I tried to introduce some kind of complexity in the facade. That's why it does a bit of a zigzag situation, where like this is kind of pushed while this is where it's really, you know, existing the way it's supposed to. And really the way is that we can also control how much that facade gets pushed by in here. So once we have all of our panels kind of ready to go, we have a cluster that we kind of created because we use this so much that kind of just reorders the point. And what that allows you to do is, if you go to any of these single panels, because you need to have the points in a very specific order before you can even push them into Revit, which is like there's no right convention, but there has to be one global convention. So at KPF, our global convention is we start from the bottom left corner and we go counterclockwise from inside out. So 0, 1, 2, 3 is how we are developing, or the KPF standard is for our adaptive panels. And once we have kind of those points ready, we can just send them to Revit using the add component adaptive panel. So we can now jump into Revit, Alex, into your family to see how the family is working. And then from there, we can start placing it.
Cool. So I guess just in terms of the workflow, the first part of the workflow is dividing the surface and getting the points to create the adaptive panels. One thing that's kind of nice and fun is that Revit, no, Grasshopper respect like the coding convention of the first number being 0. So you have 0, 1, 2, 3 are your point number. Adaptive panels does not use that convention. It uses 1 as the first number. So kind of something to keep in mind is that if you look at your list within Grasshopper, it'll be 0.0, like the first point will be 0. If you're using adaptive panels, the first point will be 1. So we're going to start off with a kind of a very basic adaptive panel. If you jump into the template files within the 2020 folder, so template files, we have the 4-point adaptive panel. It is just kind of a very basic panel here. You can see here, if I just hide these things using HH, you have kind of the very bones of the panel itself. There are adaptive points here. You can push and pull them around. The reference planes or reference lines, actually in this case, kind of are locked to that location. I've set up my keyboard shortcut for work planes here, WW. Highly recommend you do that. I don't think WW is used for anything else, so it's a good one. And these are kind of just the bones. Okay, so some important things to note. If you haven't used adaptive panels before, obviously they're based off adaptive points. If you do place a point here, it can be converted to an adaptive point by changing the point over here to adaptive. You can see it will get a number based off the other points located. So if you have 4 points and you add another one, that will be the 5th point. It just counts like everything else in Revit does. Another kind of useful thing is that if you do ever have to reorder your points, for example, if instead of going, bottom left counterclockwise, you decide to go bottom left clockwise. If I renumber this, I'm just going to delete that 0.5. If I renumber this to 2, unlike grids, views on sheets, things like that, it automatically shifts it. So it understands that this can't be 0.2 if this one is 0.2, so it changes it to 0.4. Why they can't add that to grids and views on sheets, I'll never know, but it's nice they did it in adaptive panels. The modeling environment in adaptive panels is reasonably similar to the massing environment if you're familiar with that. You can see here by selecting the grids, I have my kind of create form here. There are different ways to create form which will automatically generate based off what you have selected. So for example, if you have 4 things like here and I click create form, I can give it a thickness or just make it a single panel. So here, it'll basically just create this form. It'll give it a set distance for the offset. Okay, so here it's 2000 mils, or 2 meters. You can change it here to 1000, things like that. You can also assign parameters. So if I want to give it a thickness here, I can just create a new parameter. Obviously, similar to the numbering of the panels, it's important to have a convention. Personally, I like all caps for the thing it's controlling, and then underscore the description. So you can create kind of parameters here. You can also assign materials using subcategories. This template has a number of different subcategories. So, if you assign it to glass, you can jump up into your subcategories, which is not there. To your object styles. And then kind of start assigning your materials in here. So for example, glass, if we jump into glass here, there are no materials in this document. That was a huge error by me, not adding materials, but you can assign them there. And now this has been made, you can kind of start to pull the points around. So if I start to move these, you can see that the surface itself is respecting those points. If you pull it off axis, you can see it will start to kind of slightly curve the surface as well. So if I change it to shaded, while it's a little difficult to see, as you start to pull it, it will start to give you a doubly curved surface. Now, you can't doubly curve glass, so that's kind of not really the point, but it is an interesting way to kind of look at the creation of complicated forms within Revit using kind of 4 points. So, okay, I thought I turned off my Teams notifications. That's annoying. So at this point, what we're going to do is we're actually going to open the first Revit example. So if I jump back to my presentation and have a look at this slide here. Okay. So let's open the 2 AEC adaptive panel 4-point simple, which is in the workshop files. So, wow, I'm getting all sorts of fun pop-ups today. Okay, so Revit file. Oh, that's the overall families. The 4-point adaptive simple, this one, which I think I might even already have open. Here's one I prepared earlier. Okay, great. So, this is kind of a very basic, the basic panel that I was talking about. You can see here that we have kind of a basic form for the overall, which is the glass. If I just jump to shaded now, you can see here there's an extrusion for the glass. And then there's a sweep for the mullion itself. Due to kind of time constraints, I'm not really going to build everything live. We just kind of don't really have the time. And also building adaptive panels is insanely repetitive. So at the moment, it's just kind of a sweep of a profile and an extrusion, pretty simple. But as we kind of start to add complexity, I'll just kind of talk about the general concepts and maybe build a little corner. But as we start, as you start to do it, it just becomes super repetitive. So I'm not really going to build all of them. It's kind of important to note that using profiles is kind of a great way to create a mullion. So if I just kind of delete this for a second. Okay, and then I'm going to just hide my glass. HH is your best friend when creating adaptive components. Well, just in life generally, but creating adaptive components, you'll use HH a lot. So if I need to kind of create a profile along this kind of, if I want to create a sweep along, this rail, what I'm going to do is I'm going to go to reference. I'm going to place a point. Okay, at this point, I'm just going to hover over my reference plane. You can see it's snapping onto that reference plane. Okay, now if I select it here, you can see that it's placed it on that curve. You can see here some information about the location of the point. In this case, it's not really that important. We'll get into that later. You can see loaded into this panel, we have the mullion profile. If I edit this profile, you can see here, we have another adaptive panel. It's important to note that you can't load normal profiles into adaptive panels. Basically, the adaptive world is its own ecosystem that can live inside the Revit files, but you can't kind of jump between loadable families and adaptable loadable families. They're just built different. So when I kind of need to create a profile, I'm going to do that within another adaptive family, just a single pointed adaptive family instead of a 4-point, because it's just a profile. When you are placing points, there's a couple of ways. If you're just making something really simple, you can set your work plane. Okay. Using your WW keyboard shortcut, you can see after I do set work plane, I can then snap to any of these. Now, because it's going to be a horizontal profile that's swept around the exterior, obviously I want to set it to this one. And then from here, I can just kind of sketch. So, you know what, why don't I just delete this? And at this point, you can just sketch. So I've set my work plane. Okay, now the next kind of step is seeing where it's actually going to snap to. So there are two kind of options. One is draw and face. So if you kind of have already some geometry set up, you can see here that it'll just kind of automatically snap. We actually want to draw on the work plane itself. A profile, obviously, you don't really want it to snap off into random locations. So we're going to select that. And, then you can just use a 2-point box, something like that, to kind of get your profile. If you're just doing very quick studies, you can do it this way, where you're just kind of drawing things. In adaptive panel land, dimensions and constraints generally aren't the best way to go. So for example, if I create a dimension from this line to here, something like that. And I change my scale very quickly. If you start to equals it, it's going to start breaking. This introduces us to kind of one of the first examples within adaptive panels is the idea of offsetting points. If you have a point that you need to offset, so for example, if I wanted to, if I jump all the way back to here, which is the kind of completed example, if I wanted to create a parameter to offset from the face of glass, so the mullion sits behind the face of glass in this instance, the easiest way to do that, or the most stable way to do that, is by creating a point, snapping that point to the adaptive point, and at that point, at that time, I guess, you can start to drag that point off. Wait, I don't have 3D snapping turned on. My bad. Point, placement point. So I need, offset. Oh, okay. So I have the wrong, so in this instance, I have the wrong work plane selected, which is why it's going up. So if I reset my work plane to here, create a point. Okay, now at this time, if I offset it here, it'll start to move back. Now, basically this is the concept behind how you create, your parameters within the adaptive land. It's all about setting work planes, placing points, and then offsetting from that point. So for example, in this profile, the first offset is to create the start of the mullion. It's then offset again to get the back, and then offset left and right. So you can see here, or if I jump into my parameters, you can start to see the parameters that are linked to those points. Linking parameters is the same as anything else inside the Revit environment. If you need to link a parameter, you select the thing, and then you just click the little gray box. That's then loaded in to the 4-point panel. Okay, it already exists. Okay. Okay. Then we can place it. We're going to use WW, set our work plane, place it on the work plane. Okay. And then to create the sweep, we select the rail, we select the profile, and we click create form, and that creates the form. So that's kind of just a very basic panel at this point. It's 4-point based. It flexes. Testing is very important, obviously in all families, but especially in adaptive. And you can see that now it's basically kind of flexing around a lot. It has a profile and it has some materiality.
Awesome. Any questions you have for?
Sorry, can you please?
Oh, sorry, Rasim, you had a crazy echo, so I'm not sure what that was about.
I just heard, can you please? You can put it in the chat.
I'll follow up on the kind of stuff you guys are talking about right now. Can you talk a little bit more? I think it's one of the areas that people get really confused.
Can you hear me now?
Is
it better now? No,
it is much better. Yeah. And
how did you do a sweep for the profile? Can you just quickly remind?
Oh yeah. Sorry. Okay, so to do the sweep, it basically auto detects, which is kind of useful. So, well, sorry about that. Okay, so you need to place the location of the profile. So the first thing we did was we made the profile and we loaded it into the project. The next step is we select a point, we place it on the curve itself. Okay, so you can see it's snapping to that edge of the reference plane. Okay, now at this point, I always like to just make sure that it's actually snapped correctly. So just move your adaptive point around a little bit. Make sure that the point's moving with the line, because if you think you're on and you're slightly off, like here, you'll notice that, it's not actually on the reference plane there, or the reference line. The next step is to set the work plane. So WW, you can see as I move over, I'm going to snap onto that. That's a perpendicular plane to the curve itself. Then place the family, so drag it out onto the modeling environment, place on work plane. Then you can see it's automatically snapping to that point. Now at this point you have, your profile locked to that point. We then select the chain of reference lines. You can select one. Generally, it'll select the entire chain, but obviously tab is a good shortcut if you need to jump between a single and the entire plane, the entire chain of the sweep. Then we also just select the profile. So at this point, you can see in my selection, I have the lines and the profile. And then I just click create form. Once you click create form, Revit understands that you have a rail and you have a profile, and it just automatically creates the sweep for you. From here, you can do, add your subcategories, add your materiality, things like that, any other additional parameters you need to add. I think Timon also had a question as well.
Yeah.
Sorry.
Oh yeah, I was just gonna ask. I think one of the things that people find confusing oftentimes is working with the different work planes and offsets from those work planes. So I don't know, kind of nudging you in that direction, but I think it'd be helpful to kind of like review just how you work with offsets of work planes and when you use the global offset versus the local offsets of work planes, because that can really get people caught up. And I just think it's a good review, and love to hear your take on those spaces as much as anything.
that's actually a great point, and something I didn't cover, so thanks for bringing it up. One thing about adaptive points is because Revit they're trying to create like the most adaptive thing of all time. Once your adaptive points themselves have local XYZ planes. So they have, X, Y, and Z. You can see them here. If I just isolate this guy to have a little bit of a look, you can see them there, the blue points. Within each of those, you also have orient to. These are different options built into the point itself, which is how it creates its own localized work planes in the global environment. So when it's creating those planes, for example, you have different ways that it can create the plane. So basically, where does it consider up is a simple way to kind of examine this. There's actually a great diagram, but at this point, I wish I'd put in the presentation that I didn't, which talks about the different ways that it considers X, Y, and Z, and also the difference between instance, host, and global. I'll add it to the presentation before we send it out so that you guys have it. But the basic idea is instance is how it kind of lives within the family environment itself. So its relationship to the other points within the family environment. Host is what it's host to. So there's a number of ways you can actually place adaptive panels within Revit. We tend to use Dynamo and Rhino.Inside, which actually means there isn't a host. The host is the Dynamo script itself, which kind of becomes irrelevant. You can use massing faces, divide massing faces, and then place adaptive panels that way. And then global is just the file itself. So X, Y, and Z of your global environment. Using Dynamo and Rhino.Inside, it tends to kind of skew these ideas of instance, host, and global, because when it's placing the point, it's as if you're going around and clicking rather than locating it on a surface or something like that. In terms of Timon's question about some of our kind of advice, if you find that you're placing adaptive panel and it flips your profile, so maybe this guy is out instead of behind the glass, the advice honestly is just test it. So place one, try changing this to something else, replace it. We've had instances where for no reason at all, it'll just flip your profiles. We sent these files to Autodesk. They've confirmed that is a rare case of Revit not performing as expected. Basically, adaptive panels can be slightly problematic. So, building in a parameter to allow for the rotate. What we ended up doing in that example is we had, I think it was like 6 or 7 panels where the profile sweep at the back of the panel mirrored itself to the outside. So the way we got around that is we just built an instance parameter which flipped the profile. It can be slightly problematic in those kind of times. So, you know, if you are kind of having a little bit of problems, definitely look at, you know, the way that your point, like the style of your point, the orient of your point. Maybe look at flipping these around, trying host XYZ, trying global XYZ. I've found that if you kind of flip between the instance and the host here, these ones don't perform, you know, kind of very well. Ultimately, global Z and host XY is what you would kind of like, because then it respects the vertical height but orients to the facade. However, these are pretty problematic, which is why, you know, in a further example, we actually kind of start to remove these and control the back face of the panel by using additional points. We found that, you know, if you can control the placement of the points, that is very stable. The relationship of the geometry between the points is also extremely stable. So we started to basically strip away some of the automatic things built into Revit to just control it manually ourselves. Well, parametrically, not manually, because we just found the performance and the variation, the Revit, you know.
The risk of inconsistency is
That's
too
a
high.
very diplomatic way of saying what everyone knows I was trying to say.
And,
thank you.
So you're kind of saying that you're like, basically, I mean, I'm going to make it up, but you're kind of putting 8 points. You're like saying, I'm going to put 4 points and then I'll put my depth points. And then I obviously know which way it's going to rotate. Maybe not 8, maybe 5 or whatever your number comes out to be. That's a really clever way of getting around it.
Yep. That's exactly how we did it. And yeah, we just found it's really kind of, it's way more stable, especially because, you know, for some of the examples, especially in TCC, if I just jump to left, no, here we go. In TCC, okay. You had this kind of condition where now I can't get my Revit to work. Come on, Revit. Okay, let's get these points. TCC, you kind of had examples like this, where the panel itself was slanted in this direction, which means these vertical mullions on the side were leaning back. However, when you kind of build a slanted facade, sorry, my mouse DPI decided to change just for fun. However, the horizontal mullions, they need to be fixed to the slab, so they're not slanted. Trying to build that into an adaptive panel, especially over those, you know, 9,500 unique panels, was just started to become a bit of a nightmare. Adding those additional panels at the back to control, you know, the flat horizontal mullions and the slanted vertical mullions just seemed like the easiest way to do it. So yeah, that's kind of how we started off with a kind of a very simple panel, adaptive panel like this. We introduced a transom, and then we kind of pushed forward and started to add additional points to the back. So for example, 8 points for the vertical, for the flats, and then 12 points for the curved. So yeah, that's kind of how we started to deal with it. Great question. Thank you.
Yeah, thanks.
Cool. So thank you for, I'm sharing the right screen, Alex?
Yep.
Okay,
yeah.
Cool. Thank you for the in-depth knowledge on adaptive panels. So now once we have our adaptive panels ready and we have the grasshopper, you know, kind of condition ready, now comes the time to like make everything come together inside of Revit, for which we're going to be using Rhino.Inside. I generally always make sure that the points are ordered in the correct order before I push the button on the adaptive component, because if, you know, you're putting in 9,000 panels and the points order is incorrect, that means all of your adaptive panels are going to be wrong. But in here, because everything is kind of already set up, you can see that the points are ordered correctly, the way they're numbered is correctly. We have this particular look kind of output just to QC the points, and this to just make sure that the point list kind of comes in correctly. And in case there's anything going weird, we try to QC as much as possible inside of Grasshopper before we even push the button inside of Revit, because Revit, once it starts working, the only way to end of process is to crash it, which is not an ideal situation. So in any case, coming back to the point. So once we have the add component kind of node available and the type node. You can make sure that the node kind of is selecting the AEC 4-point simple panel, which you can right click on the type and go to the different categories. The way this works is exactly the way things are ordered inside of Revit. So inside of model categories, you can choose the object style of the category and then do the particular type. And we're ready to place the points. So I'm gonna give it the points, and I'm gonna give it the type, and it's gonna crunch. And that was 1.5 seconds, which is good. And now we have our adaptive panels already placed inside of Revit. And as you can see, if I unpin it, the order of the point is exactly the way Alex intended them to be placed. So we've kind of made sure that happens, and the facade is kind of, working the way it's supposed to as well. One of the cool things that I've kind of noticed inside of Rhino.Inside is that till the object or the element that you're creating inside of Rhino.Inside and this is only valid for the same session. So Rhino.Inside does not element binding for, like, if you do something, you close out and then you reopen the Grasshopper file, it's not going to remember that. But for the same session, if your geometry is pinned, then everything inside of that geometry is still being controlled by Grasshopper or Rhino.Inside. If it's not pinned, then everything is kind of free to go and you can modify it. So if I kind of unpin it, I can move that around for if there's a need to fix something specifically in there. So that's pretty much how you place a very basic curtain wall panel inside of Revit.
So one quick thing to bring up about the element binding and why that's a important thing to note is that Grasshopper flows from left to right, as most visual programming softwares do. The reason that this is super important to understand is that Rhino.Inside doesn't use the baking method that Grasshopper does. So what that means is if at this point we designed this facade, we placed the panels, everything's looking, beautiful. If we were then decided to jump onto another facade and we're utilizing this same Grasshopper script, which is, based off a curve, if we select a different curve, Grasshopper runs from left to right and then creates the panels at the end. It will delete the panels from the first facade as it creates the panels for the second. So while element binding doesn't exist, what Aniket was, kind of bringing up, and I just wanted to say it explicitly because as someone who's run this, switched a panel and then realized all my initial panels got deleted, if you create the panels within Revit and then reset something at the start of the script, literally anything, it will then recreate the panels. At that point, it will delete the initial set of panels and create the second. The way around that is either 1, unpinning the panels, 2, closing Revit, reopening Revit, breaking that kind of bind between Grasshopper itself and the panels, or 3, freezing your Grasshopper and doing the old copy paste. It's definitely not the prettiest way to work, but if you have all, sometimes it's just simpler to have, west facade, east facade, north facade, south facade as 4 different blocks based off 4 curves, and then just setting them one at a time. They're kind of your 4 options. Obviously, make sure you freeze components you're not using, cut down your computational power, that kind of thing. And then the second point that Aniket brought up is that once you close Revit, the kind of downside is if you then need to replace all of the panels, it's broken the bind. So 9,500 panels behind me. Deleting those also took a lot of time. So Nick, as part of the script, he also allowed for the deletion of panels. We were lucky enough to have a separate machine that we just kind of ran this thing on for 2 hours, and part of that was deleting all the additional panels and then replacing them all, because if you forget or if you accidentally have a work set closed and you run the script and you don't know why it worked and you freak out and you close Revit and reopen it, your 9,500 panels turns into like 27 or 2850 very quickly as it just kind of duplicates. So just kind of keep that in mind. They're talking about adding element binding, but it hasn't happened yet. Question about creating the profile in Grasshopper. You can't create geometry, parametric geometry inside the adaptive environment within Rhino.Inside yet. Creating those relationships between the points hasn't been added. So you could kind of use Beam or something like that to create the geometry and then just bring it in. But if you are looking to create kind of a fully adaptive system within Revit itself, you can't do that using Rhino.Inside yet.
Yeah.
Okay, so starting to add oh, sorry, did you have any?
No, not really. I was just gonna share the next slide.
Oh, cool.
Yeah. So adding more complexity, we were gonna create some more data and put that data inside of Revit, but also make the panel a bit more complicated. So eventually the goal is to be on the second diagram, second image that you see here. So if I go to my normal run,
I've got to do the Revit bit first, mate.
Oh, sorry.
All good. Okay, so adding more complexity, as Aniket was talking about here. This is the second file in the workshop files. It is 04, the 4-point panel with a transom. So like I kind of said, I'm not going to build the whole thing. I'll just show you some of the key ideas. So if we jump back here, this is the initial panel I was working on. It's just the 4 points. Now, the first part is kind of dividing the surface. So if we needed to, just going to hide these. If I wanted to add a transom, you're going to need points. Everything in adaptive panels is based off points and lines. And lines really are just 2 points with a line in between them. So the first thing I'm going to do is add some points to the curves themselves. Okay. At this point, flex, just make sure everything's working. Okay, so now we kind of have our points placed. Then we're going to connect them with a reference line. Okay, so select the reference line. Make sure you have 3D snapping turned on. If you don't, it's going to base it off a work plane. Okay, so I'm going to turn on 3D snapping. Now you can see as I hover over the point itself, I get that circle showing that it's snapped to that point. And I can connect the points like this. Okay, now at the moment, you can see that my transom is, let's just say it's a unique design. So what I need to do is kind of make it flat. Okay, I've selected this point, and now we're going to talk about length along curve. This is a pretty important concept within adaptive panels, and it's how you basically measure length. I discussed it a little bit before, but there's two basic methods. There's normalized curve length, and then there is segment length. Okay, normalized curve length basically draws takes the entire length of the curve and then uses a fraction along that length. So the start of the curve is 0, the end of the curve is 1. Segment length uses kind of real world lengths. So for example, here you can see it's 4 meters. Obviously this panel is, insanely huge. If that is 4 meters, I can adjust it here. So if I change it to 2 meters, you can see it moves down. It's also kind of important that at this point, you can see that this is the start of the curve and this is the end. If this is 2 and this is 4, then the height is, probably about 6. I guess it's kind of not that big. So how do we need this to work? Now, you can do either, and it really just depends on how you kind of want to design your panel. But let's start with segment length. Okay, so let's just say I want the transom to be 1 meter from the top. Okay, so you can see if I change this to 1 meter here, and I change this to 1 meter, so I change this to segment length also, and set it to 1 meter, that's 100 mils, good work. Okay. Okay, sure. You can see the issue is that as the reference lines were drawn between the points, the start and the end are in different locations. Here, the start is at 0.3 going to 0.2. And then from this one, it's going from 1 to 4, okay? So the way that Revit kind of deals with that is if you select this point, it also has the measure from, okay? Measure from allows us to switch it from beginning to end, okay? Now I can reset this to 1,000. And it will maintain that. If I pull it up, it's always maintaining that 1,000 offset. If I stretch it sideways, it maintains that 1000 offset. Okay, this is kind of a very simple way to create, just basic, basic divisions of surfaces. At that point, I'm going to hide those. I need to create a chain around the outside. I then draw my lines in here and here. At that point, I can select a chain. I can click create form, and it's exactly the same as the first example. It creates the forms. I can create the offset. I can parameterize all of this if I want to as well. So if I wanted to, create a parameter for the offset of here, I could select this and just assign a parameter. The second example is, instead of using a segment length, is to use a curve normal length. Curve normal lengths are great if you do a lot of slanted panels, and I will show you why. Okay, so once I change it to segment length, you can see it now becomes a fraction. Okay, the reason that that is important is because as a panel starts to slant here, you can see that this is now no longer a meter. It's a meter on the right angled vertical line, but on the angled line, you're now starting to get into trigonometry. It's now no longer vertical. It's now no longer a meter. It's, the angle using this distance here to get, using, those two distances to get that distance. A kind of easy way to get around that is to use the normal length, because if we look at it as a fraction, this distance as a fraction of the overall is actually the same here. So because the line of the length is incrementally increasing as the panel shifts out sideways, the fractional relationship between this part of the transom here as a fraction of the overall length remains the same. The way you can kind of just see that, like more basically, I guess, is if I just create reverse caps, great. Okay. If I just create a parameter, we can start to play with this number here, and you'll see it kind of in action. So let me just pull this over a little bit. So if I change it to 0.5, which is going to be the middle, and I hit apply, this is, halfway between those curves. It kind of actually does look like it's shifted a little towards the top. This segment's actually bigger, but that's just actually kind of a little bit of an optical illusion because of the points. That's actually the center, but you can start to kind of, just change these like this, change the number. So you can start to use Grasshopper to kind of create your lengths, maybe as an instance parameter, add these parameters in. So the next example we're going to look at is going to involve taking these data points and then bringing them into Rhino, and then using Grasshopper to kind of set the parameters. Something else that we should talk about is the fins themselves. While adaptive panels are kind of great, they're pretty complicated. We've only just started to get into them. You can see there's a bunch of Orient 2 things going on. You've got curve lengths, you've got normal lengths. Giving these to a team sometimes can create, you end up having to help out the team because the system that you set up can be quite complicated. For TCC, what we ended up doing is there was a lot of kind of play with the facade fins. The panels themselves, while they changed, didn't change that much. They were pretty stable. However, the patterning of the fins themselves did change a lot. So what we did is we started to separate those two. It started off as an integrated system. However, as we kind of progressed down the line, we separated the fins out of the panels themselves. And the reason we did that is, one, for runtime. If you wanted to recalculate all of the fins, if they were separate from the panels, it's going to be super fast. Okay, if they're integrated into those panels, it went up to about 4 hours for creating the entire tower, which does not lend itself well to, iterative design. What we did, by separating that out, you could run all of the fins in around 20 minutes and the panel stayed the same. This allows for ABA rhythms, attractor points, things like that. The way we ended up creating the fins themselves, we're using a structural column. Structural columns are great because, one, they're super easy to use. Two, they're profile based. So you can just sketch a profile, load it in. And three, they can slant. The fins, while they're only leaning in one direction, they're not twisting. There's none of that. Structural columns are a great solution for this. It allows you to just quickly run it over an entire facade instead of getting kind of stuck building it within the adaptive panel themselves. And it also allows the team to quickly kind of iterate through designs. If you kind of give an adaptive panel and ask someone to update a profile, there's a way higher skill needed to complete that task than based off a structural column. If you have a structural column and you don't even need it to be adaptive, you know, you're just creating an extrusion at that point. You can come in here, you can just ask a team member to draw whatever they want in here, adding, you know, kind of complexity. Maybe you have like a little, you know, something like this. My trim's not working. Here we go. You know, it's just as simple as, you know, kind of adding in an extrusion, and then once you kind of bring it into Revit, it respects that. It's a great kind of workaround, both in terms of performance and usability for the team. So now we're going to jump back to Rhino, and Aniket's going to place the panels.
Yeah. So you see the red screen, Alex?
Mm-hmm.
Okay, cool. So very similarly, we're going to use, I mean, the script kind of remains the same. We're going to take a surface. We're going to break that surface down into 4 individual points. And those points are going to be our ways of visualizing the geometry in here and making sure that it comes out correctly. But there's also another aspect of it going on where we have kind of isolated the vertical lines, and we're going to be placing fins there. So you can see that I am breaking that panel and isolating just the unique lines, and we're going to be placing fins based on an attractor point solution, which is kind of going on here, and it's been mapped so that it's kind of creating values that the parameters of that particular fin can accept, which is somewhere between 100 and 500, I believe. Yeah, 100 and 500. So really not that difficult. We just are going to connect some wires. So we're going to connect the point in here, and again here, make sure that you have the gloss transom panel selected. So if I go to model and I go to category filter, go to panels, and I'm going to select the gloss transom, just going to attach a panel here to make sure that it's correct, which it is. So I can place all of my panels right there. And now comes the addition of the fins. So I'm going to select the fin type. So I'm going to go into model, and we generally model all of our fins as structural framing, or no, sorry, structural beams. No, it's not structural beams either. It's just structural columns. Oh, there you go. No, I don't have that family loaded. Sorry, that's completely on me. That is also not the right location for it. 2000 families. So make sure that you have the ST fin family kind of loaded in to Revit, and everything's gonna now, of course.
We'll do it live.
I mean, I can use your. We can use a different. Oh, it did load. Okay, awesome. All categories model. Category is structural framing, ST fin 2 point. So just gonna attach a panel here just to make sure. I have had a lot of bad luck where I put in the wrong thing in the wrong node. So I'm always double checking my work. And that's like, that just goes for everybody. It doesn't hurt to be a bit more careful with what you're putting in. So I can connect the type, I can connect the curves, and as you can see, it's gonna place all the fins. And these fins have an instance parameter going in there, which is being kind of controlled by the integers. So this is a kind of a not the best qualitative example in terms of design quality, but this kind of shows you what all can be done by just utilizing a couple of nodes inside of Rhino, and inside of Grasshopper, and how you can kind of control everything inside of Revit based on that. So if I change like the location of the slider, you can see that all of these are being updated. The updating is not that huge, so the design iteration doesn't look like much. It will. Now you can see it. So yeah, that's pretty much it on how you can place fins and adaptive and a more complicated adaptive panel inside of Rhino.Inside using Grasshopper.
It's
Sorry.
sorry. It's also kind of it should be noted that this is a pretty small example. So if you want to start playing around with sliders inside Grasshopper and it's a big facade, definitely look at kind of freezing, freezing out the creation of the Revit geometry. As you update the sliders, it's recreating all the instances every time you update. So, like anything with Grasshopper, save often, or Revit, or any program, I guess, really. Save often, freeze things you don't need to be computed at the time, and then unfreeze them when you do want it to run again. Rhino.Inside, you're seeing the geometry inside Rhino as well. So you can freeze the creation of the Revit geometry, play around with your parameters, and then just create the Revit geometry after. It'll be a lot faster.
That is good logic. Yeah. We can just jump into the slide, I believe, now, because we're gonna run out of time.
Yeah.
We have 10 minutes. Screen one. Okay. So
okay, that's us. So unfortunately we've kind of run out of a bit of time. This is the next kind of step was to create the 8-point panel. We're giving you guys all these files, so feel free to jump in and dissect them. As you kind of start to add complexity, what we start doing is we start also loading in families. So in the very first example, you saw the profile come in to create the sweep. In the second, and so as we started to add the 8 points, and as we added the transom, we had to add that additional line and then kind of recreate the chains to create the profile sweeps around the outside. As it kind of added in complexity, what we ended up doing was we just built an additional family and loaded it in. It was just a 4-point family that had an extrusion within it, which allowed us to then just click the points and place them in the adaptive family. Actually, Aniket, can I share my screen for 2 seconds?
Yep.
Okay. So here's kind of the 8-point panel that I was talking about with Tim on before. You can see we've added additional points on the back face to control the depth. And then you can see for here, instead of basically having reference lines everywhere, what we've done is we have an additional family here called 8-point. And then instead of kind of creating it natively within the family, you just place it on the points. So if I go to place this, obviously isolating is way better than just, having everything turned on. But at this point, if I just place my points like so, it's going to create the family and snap it to those points. That was the wrong one, whatever. The nice thing about this is it kind of lives with the outside, so it's very easy to update. But as you load it in, you just need the points. You don't need the reference lines as well. So that's kind of an important distinction with adding additional kind of detail to some of these families.
You have like a skeleton and then subfamilies kind of just placed on it inside the project.
Exactly. Yep. So you can see here, it's basically the whole thing. Inside the 8-point is just the reference lines and the points themselves. So you can see here, all built with that same logic: normalized curve lengths, offsetting, connecting with lines, snapping to points, and it's just the framework itself. Then from there, if I just hide reset, all that stuff, this is just this single family, super simple. It's also 8 points, which allows it to kind of flex with that framework. It's just a straight extrusion between these two. So the way I created that is it's basically just a sweep, a loft between the two surfaces. It then has a parameter for the material. Once it gets loaded in, which is this one, oops. It then just snaps to the points, and each of them either has a type that then gets pulled through for the materiality, which is kind of how we start to build the 8 points. 12 points, which we won't get to because we've run out of time, is exactly the same kind of idea, where you just add an additional point, and then the family you load in is also a 12-pointed adaptive. Building the framework is kind of a lot easier than trying to build all of the geometry within the 8-point panel itself. Also, another thing that should be noted, I guess, which is kind of complicated, is you can see here that the depth of this starts to kind of skew out a little bit as the panel, if you like flex it to its kind of super, to the kind of ends, this distance, it actually gets thinner as you start to increase the angle between the two panels. You can see that this distance isn't fixed. Now, when you're building this with a real, in the real world, that's an extrusion that then kind of just gets cut and set in. So if you want to kind of control this in a more accurate manner, you start having to introduce a little bit of trigonometry, which we won't get to because once again, ran out of time. But basically what you need to do is you need to look at the angle between the front and the back, then create the distance. And then from there, you can start to use like the fact that Pythagoras triangles mirror themselves as they get bigger and start to look at offsetting your distances. That was all like way too short for the amount of complexity. If you do start to get into maths, hit me up because I love this kind of stuff. But yeah, there's as you kind of get more and more complicated, you start to add more and more complexity into the panels themselves. And once again, pulling out the geometry and just having the framework to control some points is a lot simpler when you're actually working the files.
Awesome. So as Alex already mentioned, we were also planning on doing a 12-point panel, which we didn't get to. Well, we didn't even get to do the 8-point panel, but that family is already in the AECtech folder, and I believe so is the Grasshopper file. So it should be available for you to mess around with actively if you want. In case there are any questions, do reach out. We'd be more than happy to assist you with anything. Now, this is a lot of content, right? So the next question is, what are the resources that are kind of available, and what are the next steps or possibilities with Rhino.Inside? Within recent hops introduction of hops component, you can now run CPython libraries inside of Grasshopper to analyze data that's inside of Revit. Since Revit is basically a relational database, you can run any kind of data analysis in there using NumPy, SciPy, Pandas, or Matplotlib. There's a great Your Desk University tutorial on this and how I believe Smith Jr. is doing stuff with this by, I might be pronouncing his name incorrectly, but by Leyland, which might be a good place to turn to understand what are the next steps for Rhino.Inside. Rhino.Inside, this is just to showcase what all exists in terms of backend support for Rhino.Inside. So Rhino.Inside has an amazing guides page where you can go to the guides, and it's kind of broken down into much more simpler logic and how you can utilize each of the nodes inside of Grasshopper that are Revit based. And then they also have a huge support on the RIR discourse channel, which is if there's any problem that you're having with Rhino.Inside, from installation to geometry specific problems, you can reach out to the discourse, and one of the developers from the Rhino.Inside team is going to reach out to you. One thing to note is that it's still in beta. Earlier, they were planning on releasing the 1.0, and this workshop would have been a mixture of KPF and McNeil presenting that 1.0 together, but they did not release 1.0. So it's still in its beta version. It's on 0.9.7, and it's still expiring every 90 days from the date of release. Talking about resources, so if you go to Rhino.Inside, the beta discover page, any and all Rhino.Inside presentations that are being done outside the world that are approved by McNeil is kind of there. There's also GitHub that's available for Rhino.Inside to analyze any and all the code. Marcelo has an amazing book on how Dynamo and Grasshopper work inside of Revit. And we need to give a shout out to Gavin Crumph, our CPM guru, who is one of the few people to have tutorials not only on how to do Rhino.Inside Dynamo, but also how to do adaptive panels. So you can go watch that as well. And in case you have any questions, you can either reach out to the individuals who are presenting that content, or you can reach out to us. It's not an issue at all. I mean, Gavin and Marcelo are really on top of things, and they're always happy to help individuals in case there's a question. So our contact information, we'll share this the slides with you. We can find both of us on LinkedIn by our names. Alex being a bit more of a bigger BIM geek than I am. His handle is BIMatics and mine isn't. And thank you. Happy BIMing. In case there are any questions, you can ask us right now. We have a total of 1 minute. I believe there's something in the chat. Oh, yeah, feel free to drop off if you don't have any questions.
Thanks, guys, for all the time you put into this. I do think there was a lot of really good content. I think people who maybe haven't worked with adaptive components, they might not know how beneficial some of the pieces you guys shared about, but obviously the experience and stuff you guys are bringing to this is really great.
Yeah, it's definitely a whole world that, like, once you jump in, it's consuming. If you think Revit's complicated, like, it's amazing the amount of complexity you can create with points, lines, and extrusions.
I kind of appreciate how you guys started with different projects, showing the different variations between the projects, because I think that's the thing that's kind of confusing sometimes, is the nuanced variations and how everything has to be customized. We think we can do like one thing for everything, but even a square panel can be complicated, right?
Yeah,
because of the
totally.
nuances we're looking for. But
Totally.
yeah, it's been good to be at this conference together.
Yeah.
Hi to everyone else out there, and I guess we'll see you maybe at the next workshop or on Monday.
Totally.
I'm skipping the hackathon this year.
Oh no.
Yeah, I need sleep, man. I'm getting too old for that kind of stuff. Thanks, Timon.
Thank you,
All right,
Timon.
guys.
Yeah, bye-bye.
Bye.